what we're going to report on, what we're going to share today, is in collaboration and sort of complementary to the modem work. It's work that really needed to be done, and it's things that we've been talking about for a while. So Paul is going to speak to that directly with some artifacts and some graphics. Then we'll answer questions, and we're also actively soliciting some feedback on some of the decisions because they are the parts of the design that are closest to the operator, and that has a lot of weight and importance to it. So it needs to be discussed and kind of brought up to the surface and presented and distributed as best we can. And we're getting to the point where we can start, I think, sharing the what the user interface for the radio will be. Still pretty crude, but we're getting close to the point where we can share it. Welcome, everybody. This is the 10th of June, and this is the Open Research Institute's FPGA projects meetup. And what we do here at this meeting is we talk about what we have done and what we have planned to do over the next week or so. If we have any particular roadblocks, anything that's really in our way, causing us trouble, and if we need any resources that ORI can help provide. The work that we're going to discuss today is being done in support of and in parallel to the modem design. So we're essentially kind of bringing up to speed the human radio interface part. So up until now, we've spent a lot of time talking about the actual modem, the manipulation of the data to the waveform, and getting that working. And as you've seen, it's demonstrated and largely working well. Matthew's identified some bugs, some things that he wants to fix, but we have a very stable waveform. It's actually still going on in the lab and has been up and running for weeks, and a lot of work has been done here for a good open source design. So I'm going to turn it over to Paul to talk about the work that's been done for the human radio interface. Lots in this part of the design. This is where we decide the priority of the different data flows, like you have voice and control messages, which include authorization and authentication, text messaging, and bulk data transfer. Those are all the things that we would like to incorporate and make happen seamlessly and with as little interruption to the operator as possible. So take it away, Paul.
Okay, as Michelle said, what we've been doing is working on the interface between the modem and the device, whatever it might be, that provides the user interface to the user, which includes the microphone and the speaker and a keyboard for typing chat messages and a screen for seeing chat messages, and probably some kind of data interface to maybe a virtual one to the network at large, so you can send other kinds of data through the modem. So we've gotten a lot of progress. Michelle built a little interface that lets you push to talk, and the host is being emulated by a Raspberry Pi, which is plenty of Raspberry Pi 4, and which has enough power to do all this and more to spare, I think. And then the modem is not being emulated at all at the moment. What we're doing instead is encapsulating the frames that the host would be building for the modem in UDP and sending them over my LAN to another computer, which happens to be this one here that I'm talking to you on, and um, displaying as much as we can of the data and using Wireshark to capture the rest of it, and working toward a design that would allow you to build a radio, an opulent voice radio that has all these features, whether in one integrated thing or in two parts, one for the head end and one for the back end modem. So we've got a prototype of some of that radio here, but we're not trying to worry about anything the modem is definitely going to do by itself, which includes all the forward error correction and the scrambling and the whitening and the coding and the modulation and the sending and receiving and all that stuff. That's not happening in this emulation. We're just sending the bits and getting back bits and trying to make sense of it all. Let me share screen here and show you a whiteboard diagram. So this is 140 milliseconds, which is our opulent voice frame time, in sort of three separate views, A, B, and C here. Um, the basic view let me talk about first is view A. Every frame has a dedicated header, opulent voice frame header, which is 12 bytes long in the baseline design, and it's protected by GoLay codes when you transmit it over the air. And then the payload, which is the rest of the 40 milliseconds. And that's where the good stuff goes. And it gets a Viterbi code. That's right. So both are error corrected, sort of similar strength, but the frame header can be decoded by itself quickly because the GoLay coder is pretty simple. So it gives you an advanced peek at the payload. And that if you had a high Faria style architecture where the satellite was receiving many channels of this opulent voice modulation, then it might be able to get away with just peeking at the frame header. The frame header contains the claimed station ID, which is encoded in 6 bytes and lets you have room for about 9 bytes of uppercase text and digits and a couple of punctuation marks, so you can make call signs out of it. And then it includes a 3 byte token, which is computed cryptographically, and it's part of the authentication protocol that we sketched out a few years ago for this whole system. So between having sender ID and having done some previous cryptographic conversations with the sender, it can authenticate that each payload comes from who it says it comes from. Now that if you look at row B, um, this is a breakdown of what a typical Opus voice packet would look like in this system. It has the frame header. It also has network headers, the IP, UDP, RTP, which would typically wrap an Opus packet if it were being sent over the internet or over wires or whatever, anything over, besides opulent voice. And we've chosen to adopt that protocol, even though the overhead is a little bit onerous, so that we can just be interoperable directly with all these other things. And then the Opus vocoder takes 40 milliseconds worth of voice samples, sort of wave file kind of samples, just PCM at 48 kilohertz, and crunches them down using its magic to an 80 byte constant size packet. Okay, so if all we were doing is voice, that would be all we would need, and we'd be done with this part of the tutorial. But we also want to be able to do these chat messages sent from a keyboard during a voice conversation. We have a small set of control messages we need to be able to send in order to interact with authentication and other functions yet to be designed of the host satellite or ground sat or repeater or whatever it ends up being. So we need a way to multiplex different kinds of data into this same format. And what we designed here is a stream of packets, which are considered to be all interchangeable at a certain level. Um, and then the coolest way that we could find to delineate the packet boundaries is something called COBS, which stands for consistent overhead byte stuffing. And this is a replacement for the older, more primitive kind of byte stuffing that you may have run into before in protocols like SLIP or the KISS modem, uh, KISS TNC for packet radio, where they stuff in bytes wherever it sees something that it can't handle as a binary. This is a smarter protocol. It only adds a tiny bit of overhead and it never grows to a large amount. Whereas SLIP, you can have up to 100% overhead. This tops out at a percent or two and is always consistent and very simple. And that the only thing you need to know about it for the purposes of this discussion is that in the data part of a COBS stream, there are no 0 bytes. And in between packets, there is at least one 0 byte. So a stream of non-zero data followed by a zero is what you're looking for. You pull that out, run it through a very simple decoder uh, to put the zeros back where they belong, basically, in the original data stream. And now you have a packet that's been fully delimited. So this is the same diagram, just extended out to multiple packets. Uh, every 40 millisecond payload has the frame header and the payload, the frame header and the payload. And what we've in view C here, we just labeled it more because we have Cobb stream data in every payload. Now, here's where it gets interesting in view D here at the bottom. The red lines represent the 0 bytes that delineate packets in Cobbs, and the orange rectangles represent whatever headers that packet has. So if it's a voice packet for Opulent Voice, it's going to have IP, UDP, and RTP headers. If it's a text message, it's just going to have IP and UDP. If it's some other data, maybe from the network to network traffic, it may be anything. It could be TCP, or it even could be some of the management protocols, or whatever kind of stuff you could send over the internet. And this is just one possible packing to give me a chance to talk about some of the ins and outs. In this particular scenario that I've drawn, the first full frame is a standard Opus voice frame. So it starts at the beginning of the frame, has the IP, UDP, RTP headers, and the rest of it is Cobbs encoded, but it's just the Opus packet. And at the end of that frame, there's a 0. And that completely fills the entire frame, and that's why the frame is that size, because the voice exactly fits in there. In the second frame that I've drawn, I see uh, all of a short packet and the beginning of a longer packet, which has been packed in with it. You can see again, there's the headers, there's some data, which we haven't drawn anything here to represent, and then a 0 at the end that says, okay, that's the end of the packet. And immediately followed by the beginning of the next packet, which has its headers, whatever they are, and then more bytes than will fit in this frame. And those spill into the next frame and even the frame after that. And when you finally see a 0, then you have the whole longer packet. And if some voice comes along, you probably want to prioritize the voice. That's what we've decided to do, is give the voice absolute priority over everything. Um, and we've also chosen to wait until a frame boundary. So we put in some 0 padding, which just is the Cobb's way of saying no data is happening right now. And then at the next frame boundary, we start again with protocol overhead and the voice packet. And we can go on for as long as the speaker can stand it, or until some kind of timeout kicks in. Um, we could do the same thing between the short packet and the longer packet, and that would be easier. Um, but obviously it costs overhead for no particularly good reason. So I'm thinking that we'll try to pack the things that aren't voice into the Cobb stream as efficiently as possible. Now, remember, as I mentioned before, we're encapsulating each of these frames into an Ethernet packet and sending it between our Raspberry Pi and our emulated modem, which eventually would be a Pluto SDR, but is now currently just my computer dumping out what it sees. If you imagine those as being part of a radio in a box, or a radio that you bought as one unit, that Ethernet, or whatever it ends up being, could be any kind of physical interface, is going to be very short and very reliable. It's just going to be a wire. So you can rely on every packet's going to get through, or almost every packet, and they're not going to get out of order. If you had some more between your two boxes, like maybe a whole internet link, like if you had your head end with the microphone and speaker and everything in your shack in town, and you had your modem on the mountain, trying to get better range out of your for terrestrial work out of your transmitter, or at least someplace where you're allowed to have an external antenna so you can point it at the satellite. Those guarantees might not be true. So we had a discussion about what to do about that. Um, it's pretty easy. It's well-known technology anyway to take packets that get scrambled up and arrive out of order and reassemble them in order. But it's a little bit messy and it can add delay, and um, it's not needed for the case that we think we're targeting, where mostly the two hosts are right next to each other. And by the way, it's a wheel that doesn't really need reinventing. You could just use the TCP capabilities that are in your host computer's existing network stack, which already has guaranteed delivery and has reordering data that comes out of order and stuff like that. And it's bulletproof after decades of being used on the internet. We've made a preliminary decision to just ignore the whole problem of data loss and data getting out of order for now and implement with the assumption that everything's just going to come when you need it and you put it together in order and all you have to do is do the COBS decoding. And if sometime in the future somebody wants to implement a remote head end that's far away um, from the modem, then they're going to have to add a layer, which is probably just going to be TCP, or substitute their TCP layer for our UDP layer if they want to save a few bytes. We've talked this over repeatedly, and I think this is a good decision. If anybody sees a problem, it'd be nice to hear about that sooner rather than later, so we can redirect. Um, so think about that and give us your feedback.
A good idea to maybe we have a general idea about the amount of overhead difference. So a naive fragmentation protocol for COBS. So COBS, the constant overhead byte stuffing protocol that we're using that is very useful and we're relying on it to deliver good results for operators, doesn't have a fragmentation protocol in there. Like it doesn't have one. Um, so we would have to sort of provide that. A naive implementation is about 4 bytes, but we dug in and we could get it lower. We have 3 bytes available in the Opulent voice header as reserved. It could conceivably go in there, and we could have our Opulent voice header just simply handle COBS fragmentation today. It would use up kind of a lot of that, but not, too much. But like, you could compress it and make it sort of targeted. So there is a way to kind of like handle COBS fragmentation, which is not in the COBS protocol, but since we're fragmenting COBS packets here, we could go ahead and do it. The, that would be, and again, this would be targeted towards the case of somebody that wanted to remote their radio versus the human radio interface, the interlocutor. So there is a way to do it. It's not in COBS natively, and we will write down all of this and have it clearly in the source code and in the README. So there's a sort of a clear path forward. If we go ahead and include it, the concern was, wow, we're gonna use up a lot of this 3 byte overhead that we have in there, and the reason that we have any overhead in our or any extra reserved bytes in our custom headers for Opulent Voice is because of hard-won wisdom that you really need to put in, reserved space in your protocol headers for things that you might want in the future. So if we go ahead and use it up for this, that's less reserved space. And the reason that we have this set aside is because the way that Golay encoding works is that we need a multiple of 3 bytes in order for us to completely use up the Golay encoding that we've selected. So currently we have 3 bytes. We could have 0 reserved or 3 or 6 or 9. So we've put in 3 for now, and that's a sort of an escape route for this particular function. All right, back to you.
Okay, thank you. I want to show one more screen. Okay, I just want to give people a glance at what my simulated modem looks like. This, which also be um, possibly bear some resemblance to what a user interface might look like if it's a terminal style scrolling user interface. But here this is the very startup screen. It does some initialization, and this actually is a complete session where I hit Control C before any data was allowed to come in. Now I'm scrolling down to one more that actually has some data in it. Here we go. You can see these little microphone icons. They appear one at a time to show that data, or excuse me, that show me the voice that's coming in. And then here's some text messages and so on. So that's what we're looking at. And then, oh, I lied. I'm going to show you one more screen after this one. I'm going to show you what the Wireshark looks like. There's a couple of things that are interesting here. Um, in this column mark protocol, you see it says OPV NCAP. That's a custom dissector, they call it in Wireshark terminology, that takes apart the packet and shows you what's inside that I'm in the process of writing. Um, Down here, you can see that I've decoded the frame header. There's the sender ID uh, corresponding to the call sign KK600Z and the authentication token, which we've dummied out to say bad because it's not a real authentication token. And there's our 3 reserved bytes. And you can see there's error messages here where there's supposed to be a decode of the payload. I'm still working on that. This is the first serious attempt to write Lua code because Lua is the preferred way to write dissectors. Um, Lua is not the best language for this. I have no idea why they chose it. It's kind of painful. Since I don't know anything about it, especially, it's double painful. So I think that's what I wanted to present. Did I miss anything you wanted me to cover, Michelle?
Oh, no, that's great. We did work through an awful lot of other issues with audio. Um, I think we've tried very hard to kind of capture the progress in the repos, and there's 2 repositories, and they need to be moved over to Open Research Institute project. So we started out working in private personal repositories to make sure that the very basics were working. I think now is the time to go ahead and move the interlocutor is the human radio interface, and then you have postlocutor, which is a full featured receiver. Both of these things need to be moved over to ORI, and then eventually these things will become a transceiver. So independently developing a receiver for I'm mainly doing a transmitter, but also doing parsing and having a very basic receiver functionality on my end. So I'm responsible for doing things like figuring out the priority queues and framing and making those sorts of decisions for the transmit side, and you're independently developing a receiver that then checks my work. And because the same person is not doing both of these things, we're finding all sorts of stuff. So this divergent sort of like independent co-development is working for us so far. We've gotten to the point where it's good enough to then move over to ORI. So we should probably fork the repos and then move the development over there, and then subscribe those repos to GitHub Ops channel so that people can then see the pull requests and the issues and all that sort of stuff. We have nearly 50 open issues on the transmitter. What I did is I kind of sat down and decided what were the 12 major areas for transmitter, and then I used something that's kind of new on GitHub. They took away the task list, the dynamic checkbox thing. I kind of like that, but they took it away and they replaced it with something called sub issues. And so I just went all in and embraced the the sub issue reality. It really does work. So there's a whole cornucopia of delights over there and some discussion already on the open issues. So that when you file an issue on this work, it's not that you're complaining. It's that there's some sort of aspect of the design that you want to either bring out, talk about, either decide to do or not to do. And there's lots of things that we would like to see happen with our radio system in the amateur use and outside of amateur use, but that probably shouldn't be hard coded into the protocol. So we want to be very committed to making it as simple as possible. And so a lot of those discussions need to happen now. Because so far we have a pretty simple header. It's the station identifier, and this is either your call sign or some sort of tactical call or some sort of identifier for you as the operator or the station. And then we have the claimed token, which is a cryptographic token to prove that you are who you are. And so those two things we think are the that you have to have that. There's lots of other nice to haves in a protocol, but those two things are the things that we're lacking in all of the other protocol layers, the IP, the UDP, the RTP, whatever P. And that's our special edition here. And then our enforcement of a priority for data, for text, for voice, for control, for whatever else. Differentiating out those by UDP port is how we tag the type of data. So we don't have the frame type in our header. This offloads it off to a layer we're already using, and we use ports for that. So this lets us have a lot of expansion. And we're not providing a ceiling or a limitation on the data type. It's built in right now with what we think people will use, and that part's working. We can see it working just on the LAN. So that's kind of like the overall vibe here. But there's all sorts of repeater operations, general operations, emergency communications. There's lots of history and tradition in amateur radio and in communications, radio communications in general. You know, there's a lot that would make a bid or a case for being baked into the protocol. And so now is the time to do the best effort that we can to entertain anything that really, really needs to be part of the protocol. If it can be possibly part of an application layer, great. But there is like a special role for like net control. Should that be part of the protocol or not? So those sorts of discussions are kind of opened up in the issues tracker. And I think that by forking it over to the ORI, official ORI GitHub, and then, kind of like putting it in front of people and saying, look at this stuff and tell us your opinion and think about it, that we'll get the best possible feedback over the next bit of time.
Yeah. There's a third repo that'll be moved as well, the Wireshark dissector. This will be public.
Oh yeah, yeah. Thank
Oh,
you very much for that. I'd like to also highlight that this is not your first dissector. You want to
that's
talk a
right.
little
And
bit?
not the first for this project even.
Not the first for this project. So if you'd like to give a little recap of the previous work, that'd be good.
Um, the previous dissector is for the downlink from High Faria or similar spacecraft, which is a DVB-S2. Uh, DVB-S2 was originally conceived as a video protocol for industry, for consumer video, but more recently they've added capability or improved the capability to handle data channels as well using uh, what they call generic encapsulation. Um, and but nobody had bothered to write a dissector that handled that. So there was a DVB-S2 encapsulate or dissector already in Wireshark, but it choked on data. So I added the generic encapsulation to uh, to the Wireshark dissector. I submitted it to the Wireshark project and was accepted as um, as an addition to the set of dissectors that ships with Wireshark. So if you look at the list of a million contributors who have written some code for Wireshark, my name's in there somewhere.
Yeah. GSE. That's what.
Yes, yeah, generic stream encapsulation.
Yeah, good stuff. Yeah, looking forward to this being part of it. So yeah, thank you very much for handling all of that and taking care of the logistics of getting something accepted to a big and important project.
Yeah, I will not open to suggestions on this, but I believe that what I'm going to do is not submit this dissector to Wireshark until such time as we're shipping some
Yeah,
units, so that because there's room for it to change, and nobody but us doing development on it cares about this dissector until well out into the future.
yeah, I
I,
think that's wise. You know,
I also want to relay that this is not the only proposed architecture for dividing up the station. Matthew, who wasn't able to be here today, has been arguing for having more of this work done in the fabric of FPGA in the on the modem side. he'd like to see the priority queues and the actual frame builder in there. And he's been trying to convince us. Um, so far, I like this architecture better, but there's certainly room for discussion. And the problems will be the same either way to some extent, uh, and it's much easier to prototype in software than in the fabric. But eventually, you might have radios with both designs.
Yeah. Yeah, this is a both and not an either or. I think that having a prototype working on a Raspberry Pi in Python or having a prototype ported over to C will make writing VHDL or Verilog much easier. And we've already seen several pretty big changes because once you actually take your design and use it in anger and you make it work for you, you make it perform in real time, you find out all sorts of things. So the work that we're doing now will benefit a software side solution or processor side solution on a Zinc, for instance, and will also be extraordinarily helpful as a model for future VHDL. And Matthew's generally right. Like my bias is to do as much as possible in the hardware. I like that. And you reserve for your general purpose processor things that are totally not easy to do in hardware. Like you want to reserve the special problems for special, for your general purpose processor. For the Pluto, though, with the 7010, it's pretty constricted. So for our initial implementation on the Pluto, it's okay to do most of the, do more of the work on a coprocessor, essentially on a Raspberry Pi stuck to it, and to deliver frames ready to go to the modem. When we do move to larger FPGAs or when we look at making a custom ASIC, yes, we will definitely have more room than what's on the 7010. So it's a both and not an either or. I think he's right. Uh, but for the Pluto, it's okay to do this. And also, separating it this way will help increase the number of modems available. So if someone wants to use an even smaller FPGA or a different type of radio entirely, and if they say, "Oh, you're giving me data frames," and they're already set up and ready to go, you're giving me a stream of 40 millisecond data frames in Opulent voice. Oh, okay. I can take that and I can deliver it to this extremely small, efficient custom modem or whatever. We have a good division of labor here. So it's a natural part, a natural place to kind of separate the software hardware task. We do have another modular thing that's going to happen, and that is to add a browser interface, an accessible browser interface. So the command line scrolling thing will always be there for people that want to use it. And we're going to work really hard on making this terminal interface useful, accessible as possible for terminal interface, and also have a verbose mode, a quiet mode, and a normal mode. So you get a variety. You can set it that way. But we will also have a HTML5 browser interface, and it will be designed from the start to be accessible so that everyone can use it, no matter what. So that's another sort of natural division, and that's going to follow. That's the nice thing about looking at that is after we do get this command line or terminal interface working and to a place where we are willing to share it to get wide feedback and it sort of stabilizes out, that work on the HTML interface, which will be the same functions but in HTML5, can also be independent or relatively independent. So that's another good division of labor here. So that's kind of the very high level view of it. So yeah. Oh, go ahead. Sorry.
I'd like to give my side of the religion story here. Um, I my preference is to put as much in software as you can, and the reason for that is that software is free in terms of, after you built the one, the second one is free. Um, and at this data rate, it's very likely that all of the computation can be done in software, and that leaves you with just a radio interface basically. So any kind of off-the-shelf SDR that can transmit is going to have enough bandwidth to transmit this. Well, maybe not all, but almost all will have enough bandwidth to transmit this protocol. So it may be the case that you can do this without any custom hardware. You just go buy hack RF or something like that, or hopefully they get cheaper. Anyway, um, something that can transmit with IQ samples. And I think probably a Raspberry Pi would be capable of generating all the way down to IQ samples
Okay.
for this, or something, Raspberry Pi version 8 or whatever, if it turns out to be harder than I think. And that's a great possible solution too. So there's at least three different architectures that are of interest here, and all are possible. We don't want to rule any out by making the wrong design decision.
Yeah. And as Adrian points out, it's much less expensive. Okay. No, it's yeah, both and not an either or at all. Um, and yeah, definitely looking forward to it. The past week especially, we've seen a lot of rapid progress on this. We've been talking about the priority queue and the fact that you don't have to go to a separate mode for things like text or authentication. Like you don't have to go to a separate overhead channel. We don't want data, especially, to be some sort of clunky separate packet mode. I think that a lot of amateur radio implementations of digital communications have been burdened by something that's overly separate, fussy. We don't want any of that. We've got it. So we're very confident that this is the right path forward. It's going to make it very easy to use as an operator. And the whole open process and trying to keep the protocol as simple as possible will pay off big time. And the questions about what needs to be done in hardware and software, I think we're handling as best we can. We're going to give the widest possible sets of implementations, and all of it is published. And I think by moving the work all to ORI, now's the right time. I think it's mature enough to where we can have it as a ORI repo.
Yeah. That I mean, we can't get too over the top excited about the data because it's by modern standards, it's really slow.
True.
Um, it's still super fast compared to packet radio, as usually practice in amateur radio, and not quite as fast as a DSY 56 kilobit modem, but um, definitely faster than a 1200 baud packet radio. So
For sure.
might have some utility outside of the voice realm. Rip out all that nasty analog circuitry and go straight for data.
All right. Cool. All right. Anything else, Paul?
I should give my usual speech that the remote lab is still there and working and um, available for people to do FPGA development.
Very good. Thank you. Yeah, all right. And I know that Pete has done an awful lot of digging in on these are uh, communications protocols for Earth, Venus, Earth. And if you have not yet read his part one article in the May Inner Circle newsletter, then please go to our website and check it out. It's one of the articles in our most recent newsletter. Anyway, Pete, if you'd like to talk about the your work here and maybe share the some of the more recent graphics. Those were very useful and pretty clear. You have the floor.
Oh, thanks. So the good news is part two will have a lot more pictures and a lot less math because I found some better ways to explain things. So I think that'll make part one clear as well as part two. So sort of a summary is there's three waveforms I'm working on right now. One is an FSK waveform customized for Eve. And that's just looking at what's the best FSK waveform and DMOD we can make given the link budgets of Eve. That's pretty straightforward. Low risk since we have experimental data from sending tones, back at inferior conjunction a couple months ago. So the other two waveforms are more experimental, and those are designed for Dwinolo consideration. So Thomas has been chatting about maybe sending those up on June 21st. And those are both OTFS waveforms. So the idea here is the first one is an OTFS waveform that doesn't do anything fancy. It does it the normal commercial way. And it's just to give a go on OTFS and see how does it compare to other things like Zadoff-Chu sequences that have already been done. And the second version of it is OTFS combined for the sort of mission I've been on the last month or so, which is extend OTFS and don't use it the normal way, with an equalizer and so forth to sweep up your multipath. It's to design an OTFS waveform that should focus the energy and time and delay and Doppler, focus and delay and Doppler once it bounces off the moon. So I think in all likelihood, the first FSK waveform for Eve is low technical risk. The conventional OTFS waveform for moon bounce that's low risk, and we'll see how it works. Is it better or worse than other things we're already doing? And then the third one is kind of the pie in the sky experiment of use OTFS in a new way and design the waveform so that it more efficiently transfers energy from the transmitter to the receiver. So that's kind of a recap of the three waveforms. Two are experiments in progress for over the air, and the other one is just kind of marching along for Eve.
In terms of Zadov-Chu, that's been tried with EME, but not yet with EVE.
Yeah, that's right. So there's a lot of great examples of different Zadov-Chus. And what's so neat about them is they actually have a lot in common with OTFS because, of course, when you do the time frequency correlation on receive end, Zadov-Chus have ambiguities in time and frequency, just like OTFS, pulse trains do. So there's actually quite a lot, maybe more in common with their performance than it looks at first glance. And so the idea is if we can do one experiment and send an OTFS up for 2 seconds or what have you, then we'll have an actual over-the-air experiment to show amateurs have run OTFS and here's how it works. And then the interesting thing would be to compare it to one of the other modes.
Right on. Yeah, no, that's exciting. And you're writing a series of articles about these types of communications and to sort of explore them. And so the part two is in progress and should come out maybe for June. And then in terms of like the part two and further parts, what's your feeling right now on what you're going to cover in the series?
Sure. So part one was delay only multipath channels. So part two is delay and Doppler. And so when we get into delay and Doppler, you have to customize the waveform to take account of both if you want to promote energy efficient transfer from transmit to receive. So that brings us to OTFS as an extension of that is one way to do it. And beyond part two, where it's going is basically the boost you can get from doing this depends on how well you can estimate and or predict the channel response into the future. And of course, with moon bounce, one of the practical challenges is there's a 2.4-second round trip delay. So it's not just estimate the channel, it's probably predict it. And so that may well be the heavier lift that'll take more time into the future to see if we can come up with sufficient models of multipath off the moon to actually predict that. For terrestrial channels, I think there's little doubt that this can be applied and show a benefit with it with some simple 900 or 1.2 gigahertz experiments in mobile channels. That's pretty likely. But the moon, just because of round trip time, that's an extra wrinkle that's probably pretty hard. Probably not unsolvable, but I have no idea if we can solve it this year or not.
Yeah, I think that you'd probably get like an initial immediate feedback would be, oh, well, for terrestrial channels, you're having to point your radio antenna at, who knows what. It's all sorts of multipath and the things like temperature uh, differences, weather, humidity, particles in the air, whatever, and lots of metal like structures. That there's all this, and so doing channel sounding like you do in OFDM is really super important. And yeah, you'd get like a quick feedback because usually the channel distance is short enough to where the information in the channel sounding is useful to you. And I think what a lot of people assume about especially EME or a satellite link is that, oh, if you're pointing up at a celestial object, well, I don't have to worry about any of that dreadful channel stuff on the Earth. But the problem that you're raising is that now you have this long delay. And if there is any evolution in the channel or any things that change, that this delay is potentially just as much of a challenge or just as much of a impediment to being able to design your next frame, your next set of waveforms as the terrestrial multipath channel. Would would that is that kind of the take? Like, the assumption that a lot of people have that the space channel is easy may not may not be a sound assumption.
Yeah, I think that's fair to say, because you kind of at the end of it, you're getting into delayed Doppler characterization of channels, and it's really almost nearly getting into radar imaging of the moon to make these predictions. And so that's a couple of the harder problems that after part two we'll have to think about how we might do them. The exciting news, though, when you look at delayed Doppler and things like OTFS, you end up with longer channel coherence times than you normally encounter. So like one of the simple examples of that is if you think of like VHF picket fencing, when you have a mobile channel with maybe two different multipaths. Well, it turns out the only reason it picket fences is because we're sending a CW. There's other waveforms for two path time variant channels that have, much longer coherence time, that there aren't fades, but you can't just use a FM modulated at CW. But the idea of coherence time is not really defined by channels, it's defined by channels and waveforms. And that seems to be the cutting edge of delayed Doppler channels and OTFS and that sort of thing. So there's hope that coherence time of channels like EME is longer than simple approaches would say it is, because we can prove for simple channels at least that we can get longer coherence time by doing different views of the channel as delayed Doppler instead of just time frequency. So maybe there's hope there, but to say it's a heavy lift might be a gross misunderstatement. We'll just have to see.
Yeah, no, that's exciting. Yeah, is there anything in particular that you need? Do you have like all the resources that you need to carry on and keep working on this, or any particular roadblocks that we can help solve?
Part two is marching along, and I'll clean that up and get it ready here in a week or two, I think. And the feedback was, just anything that could be more graphically explained and a little less math would carry it along. So that's in place. And then in parallel with that, I'm looking through the document on how that Opulent Voice does the MSK and the carrier recovery, which is, yeah, it's just getting up to speed on the details of that write up and see if I can follow it along. Because at some point here, if there's pieces of Opulent Voice, I might offer to help that. I've done some fixed point design and things before, so we'll see how the on ramp goes and if I can do something useful there.
Oh yeah, thank you. Yeah, any feedback on that part of the project would be great. What Pete's talking about is that what we've done is tried to write down our understanding and sort of hey, here's a PI, proportional integral controller. So there's different types of control loops, and the proportional integral controller is extremely common in receiver design, so that you figure out, what you're faced with is the clock is different from the receiver to the transmitter. The oscillators are different. There's variations, and your first job, or one of your first jobs at the receiver, is to figure out those two tones that we're getting off of minimum shift keying, two frequencies. It's gonna appear there. Where the heck are they? And we need to track them. So we need to be able to lock in. So a phase lock loop is what we do. And the way to accomplish that with the Costas loop is with the proportional integral controller. So our PI gains, you have a proportional gain and an integral gain. And we're like, okay, well, instead of just blindly testing or guessing or, it would be good enough, wouldn't it be great if we wrote down how we come up with the gains and we get as close as possible to the right gains? Because there's going to be a right answer. There is going to be numbers, this sort of amplification or gain number for the proportional term and the integral term that's going to make it as stable as possible and as quick as possible. And you have some decisions to make. You can make it respond very fast, but you may lose a little bit of stability. You can respond slower, but your result is more stable. And there is plenty of examples in radio of where you have an acquisition set of gains where you're looking over a very broad range of frequencies for the signals, those signals that you're in here somewhere. There's a pony in here somewhere, and you're trying to find them. And then, so you may want a set of gains for that. And then once you kind of lock in, then you want a finer resolution and you switch to a separate set of gains. So we know about all this in theory. When it came down to the practice of actually producing some gains for the VHDL that Matthew is writing for the modem, we were grossly wrong. And, we refined it and we wrote it down and we refined it and wrote it down. And so that document and the MATLAB live script is now, shared it with Pete. And I think it's shared on our repo, not entirely sure, but we're working on this for a little bit. So I think that I'm a little bit uncomfortable with the performance because we had to experimentally determine good gains. The gains were much larger than what the theory or what the document kind of produced. And the mismatch between the gains that work in practice over the air that perform pretty darn well, and I mean, we have a signal in the lab right now. Paul could probably walk over there and show us on the spectrum analyzer. Here's an MSK signal that's been up for weeks, working away. Like it works, but our documentation undershoots. It underestimates the gain numbers, and so when we put on our theoretical gain numbers, it's just not great. So there's something wrong with our understanding and the way that we wrote it down. There's a difference between the code and the theory in our paper, and we really want those to match. So if you see anything in there that's wrong, some sort of classic, oh, you made this mistake or that mistake, then it would be incredibly helpful to find. What we eventually want to do is publish the paper. We want it to be a good, solid introduction to, PI gain control in costless loops, why you care about it, why it's useful, to kind of anchor it into real world examples. We tried to come up with a good metaphor, which was, merging onto traffic on a freeway. If you have a car and you're trying to merge into traffic, you match the speed of all the other cars going along. And that's essentially what you're doing here. You're just trying to match the speed of what you're seeing, what you have to deal with. And if you overshoot, if you're way too fast, you're driving a jet airplane, you're not going to merge onto a freeway. If you're a horse and buggy, you're not going to merge onto the freeway. And the gains are the thing that makes you go faster or slower. So that's kind of what we're after, is to make this an accessible article that would be of interest to people that are interested in radio, that are technical enough to get it, but aren't or maybe aren't like always buried in this sort of stuff. So maybe article for QAX magazine or one of the general interest magazines would be the sort of the target for this. So thank you very much for taking a look at it. And yeah, any improvements that you see or any mistakes in the reasoning, we're using essentially Gardner, which is the kind of the backbone of all of this. Gardner's author of pretty much the book on costless loops or gain control, this sort of stuff. So it's supposed to be that approach. So if we've messed up in any way, I hope you can spot it. So thank you very
Cool.
much for taking this on and helping us out.
Oh, you're welcome. I have Gardner's book. I mean, I'll take a look, but sometimes there's like a mischaracterization of the phase detector gain or the NCO gain or something like that. So, if it was off by a bunch, maybe it's one of those, but we'll see. I'll just go through it and check it line by line.
Thank you. Very appreciated. Okay, and that's it. Welcome to Adrian. And Adrian, you have the floor with any comments or questions or or any advice for us.
Yeah, wow. Tuning in is always a deep dive into digital comms, and I'm just furiously typing away at AI and trying to get definitions on some of the terminology, since I'm really way outside my field, but it's a great learning experience. I did have a kind of a very, I apologize for naivety, question to Paul. When you described the potential loss of frames, in real world effect, what would that be? Just a gap? You would just get silence in terms of the comm?
It would depend on how long the gap was. If it was a single frame, you might not hear it at all because Opus is pretty good at handling small amounts of error. If it's a longer gap, you might get silence. Some vocoders have a tendency to go all R2D2 on you and make beepy noises when they get errors. Opus is better than that. So
Okay, just curious, what would the occurrence? And also, I don't believe that this within the implementation here would never include video, correct?
not at the state of rate.
Yeah, that's kind of what I presumed from my sort of viewpoint on it. Well, sort of tuned in. I'm actually taking a break. The Sarah's having their Eastern Conference out at the Green Bank, and I just thought I'd take a break and listen into you guys and see what you were up to, trying to sort of get an inkling as to progress that you're making. But yeah, that's about all I had to say. And gosh, it's just fantastic work that you guys are doing, and like I said, really looking forward to see what happens next year. I guess Pete, I'm working on the Eve project with DSES, and I'm really fascinated by that. Actually, the some of the European guys are over there in Sarah, the conference, not Wingalo, but I believe it's Herman, the other radio telescope over there that did the Eve reception when it was done last year, and so he talked a little bit about that, but
Oh
not
yeah, over
much.
from Stockard.
Yeah, Stockard, right, exactly, right. I just couldn't recall the name of the radio telescope, but anyway, yeah, fascinating stuff, and uh, gee gosh, I'm trying to catch up being a molecular biologist. So way outside my field, but it's I've always been interested in radio as a kid. I just kind of went to a slightly different direction professionally. But anyway, great stuff, and just wonderfully listening in.
Okay. Well,
That's
hey,
pretty much all I can say.
next time we talk, it'd be great to hear your impressions of Sarah. I've worked with some Sarah folks and gotten them like helped with forums and things like that, but I've never been able to attend uh their meetup, their meeting or conference. So maybe next time you can give us a little summary of what you found interesting from the conference. That'd be cool.
Yeah, well, they do a lot of discuss. I mean, right now, I believe some of the discussion is in what they call Radio Jove, which is the sort of HF reception of the Jupiter emissions from the Io ions interacting with the Jovian magnetic fields.
Oh
And
yeah. No, there's like a kit, right? They have a
yeah,
kit.
exactly. It's basically just in its simplest amplification implementation, it's just a HF receiver in the upper sort of HF range. Oh gosh, I don't know, 10, 12 megahertz up to about 27, which is where you receive these Jovian
Yeah, yeah.
emissions. And so, but they do some interpretation of the waves and so forth that are emitted, whether like from the north or south um, polar emissions from the Ion's a volcanic moon, and so uh, it just spews out all kinds of mainly like sulfur ions, and then these guys get trapped in the Jovian magnetosphere, and that interaction with these ions in magnetic fields, well, it's just I guess it's some kind of a like a very strange traveling wave tube or Kleisterong type of
Wow.
effect.
Okay, that's
So,
cool.
you get these high frequent. They're not microwave, but you get these radio emissions that are detectable here on Earth. And
Wow.
so anyway, so that's one of the cool things that they're talking about over there. Besides the detection of astronomical masers, that's one of the things I'm really into. And I've actually there. I don't know if you're aware of the the 20-meter radio telescope that's over there in Greenback that's accessible to the public if you have like an account with it. And 20-meter radio telescope is a pretty fair sized telescope, And so you can use that in the range of the 21 centimeter sort of bandwidth up there where the hydrogen emission line is, and the some of the Maser emissions, the hydroxyl Maser emissions. And I've been very fascinated by detecting some of those, and done some raster scans of the Orion star forming region, the nebula there, which contains quite a number of these hydroxyl Masers. And so I've done some raster scans of that just to kind of visualize the region. And those are obviously a fairly single frequency type line emitters of our 1665 megahertz, 1612 uh, megahertz, and in that range. But anyway, so those are some of the topics that they're discussing out there, besides some of the
Wow.
general astronomy stuff.
That's
One
really
guy,
cool. I
one
think
guy,
it's amazing.
yeah, this is, I mean, it's fact, kind of, really kind of a slight offshoot there from ham radio, but sort of related with the especially the equipment end of it. And but I mean, it extended, like there was even one guy that came in and talked about. I don't know if you guys are familiar with nanograv. Um, Nanograv was a study that was done to very accurately measure timing deviations from pulsars. And
Oh,
these timing deviations were related to gravitational waves passing through space, affecting the actual timing of the pulsar pulses. And so by correlating these observations for many pulsars in many directions, they've been able to reanalyze the timing changes to gravitational waves passing through the universe. And so that's kind of fascinating work that was done a number of years back. Anyway, delving a little bit more into a different topic here, but yeah, I thought
wow.
I'd
No,
take a
that's
break.
super interesting. Like, do you have time to like maybe write up a article about your experiences to share with folks through our newsletter? Because this would be like right up our alley. This is neat.
Oh, I'll think about writing something a little bit. Like I
Yeah, no,
said,
this is really cool. Like, and because you're like diving in and you're doing it, and you're doing it not like in the context of like already inured, already done this for years. You're like, you're approaching this and you're trying to do things and achieving some really cool stuff. So your perspective is just, ideal. You're
yeah, well,
That'd
a
be
bit
really
different.
neat if you had the time, because I know you do lots of cool stuff and you're very busy, but if you have the time to kind of share like your journey, I think it would be of great interest.
Well, yeah, I've never sat down and actually done this. I'm just kind of like jumping head in and just kind of being fascinated by all this stuff. And I'm just a total science geek. But as far as radio, I was actually fascinated by radio even from a kid. Love to go out to the curb. Anytime somebody threw out an old tube radio, boy, I'd go out there and grab it and start dismantling the thing.
Yep, yep.
And so it started with that, but somewhere along the line, this thing happened. It was called the Asilomar Conference back
Oh
in
yeah.
the back in the early late 70s, and I was thinking of actually going into organic chemistry. And I was actually working in an organic chemistry lab for Johnson and Johnson, synthesizing antimicrobial compounds, and that kind of, yeah, diverging from what I initially wanted to start as an engineer, electrical engineering, and then went to organic chemistry, and then just jumping around all over the place. And then the Asilomar conference happened, and I went, "Wow, this DNA stuff, genes, oh, fantastic!" And then went into that, and so I was able to follow that professionally and get my PhD in molecular immunology out of the University of Texas Southwestern in Dallas, which is where I'm originally from. But I live here in San Diego now. I came down here to work at the Salk Institute and some of the other biotech companies. But anyway, so much for my stuff. I'll let you guys get back to talking about it. And but yeah, Michelle, I'll think about writing a little blurb or something, and I'll pass it on to you if that's something that you might think of interest.
Absolutely. Yeah. No, it's super exciting and I would love, it's the sort of thing where it's like, well, I would love to read about that. And, that's kind of our vibe. If we would be enthusiastically reading it, then we want to share it with other folks like us. So yeah, please feel welcome to kind of share your perspective and your journey. And, I know that it would be appreciated.
Well, thank you very much for that inspirational interest in the storyline. Yeah, I'll definitely try to follow up on that.
Groovy.
Anyway, thanks a lot.
You bet. All right. Any other last comments? Looks like some live video of a minimum shift keying opulent voice signal.
Yeah, it took me nearly that long to get it set up because I had to install the FFmpeg on this new computer. But,
Computers, am I right?
that's what it looks like. That's running over streaming video from the remote lab.
Cool. Yeah, that's our signal. So when we talk about the modem and all of the work that we've done in VHDL to make it happen, uh, well, this is the work product right there. So it's a minimum shift keying signal, which is very efficient, has lots of benefits. And the 1 and the 2 there, that's pointing you towards the frequency 1, frequency 2. Those two frequencies, when we talk about that PI gain controller, when you get this lump of energy in your receiver, you then tackle it by saying, I'm going to multiply by these two frequencies. I'm going to do some multiplication and I'm going to do the usual, IQ extraction to get my, quadrature, demodulation out of there. And the first thing that you run into is that where the 1 and the 2 are isn't going to match up directly or exactly in the receiver as it did in the transmitter. And there's reasons for that. The clocks are different, the physical differences, drift, temperature, slop or whatever. And then also your channel can mess things up by quite a bit. So that's when we talk about having a correction or a control loop that dials it in, that pulls it in at the receiver, then that's kind of what we're talking about. This is so right there, that 1 and that 2, we need to get our receiver to match the 1 and the 2 that you see here from the transmitter. So that's in the code, and those PI gains, to make it ratchet in, to make it match faster, and to stay there, to be stable. Those choices are super important, and we want to document them correctly. We want to get the ideal results for our signal in the code. We want the documentation and the story and the explanation to match, and that's kind of what we're trying to tighten up with our article and the MATLAB model. So yeah, thank you. That's what it looks like. You can see that like the vast majority of the energy in this signal is in this main lobe. That is a hallmark of minimum shift keying. Like we're talking lots of energy in the main lobe. I see ever so often people say that you don't even really need much of a filter to filter out the other lobes, the other harmonics. So of course in practice you're still going to filter, but your filter requirements are not that harsh. So you're not dealing with a signal with a lot of energy in side lobes. You're dealing with a signal that's designed to have a constant envelope, and almost all the energy is in that main lobe. And so that's one of the several reasons why we selected minimum shift keying as the modulation that we wanted to transition to, that we wanted to evolve to. The initial design was 4-area FSK, and if you look at that spectrum, you'll see that it doesn't quite have the same picture. And there's other things that you have to care about in 4-area FSK. This is a more efficient modulation, but the thing that you kind of pay is in terms of complexity. It is more complicated to deal with, and that's been what we've been spending lots of time on in the modem design. But there it is. So thank you, Paul, for bringing that up. All right. Any other questions or comments? All right. Well, thank you, everybody. We will meet again soon. The schedule might be a little different because of travel and some other interesting things going on in the rest of June. But we'll come out with meeting times and office hours. And as always, please reach out on Slack for daily engineering and questions and comments. And keep an eye out for anything in the email list, any announcements there that we send out via email. Our website is openresearch.institute. We have daily sort of a news feed on the very front page. We have a newsletter so you can catch up with all the stuff that we do. And also the GitHub project. So all the work is there. So be looking for some new repositories to show up as we fork over all the work that's been done for the receiver, the independent receiver design, and the transmitter design. Eventually, those will be a transceiver, but we're getting a lot of benefit by having those independently developed in order to catch problems. And yeah, what I'll do is I'll turn off the recording here, and then I'm available to answer any other questions or talk about anything that anybody wants to talk about. And see you next time.